You can start, sir.
Okay. Good evening to all of you. I welcome all of you to the special lecture program today. As you know, KPA and Creactive have been arranging special talks by experts for the benefit of teachers, students, and general public. Today, we are indeed fortunate that a very distinguished NASA scientist, Asitang Mishra, Asitang Mishra has kindly agreed to give a talk on a very modern topic, namely foundation models and problem solving using data science. He is here for a short time visiting India, and he has taken out time to give this talk. I welcome him to this session on behalf of all the participants. I wholeheartedly welcome again all the KPA members, students, and their friends, as well as Creactive participants to this special evening lecture program. And I'll now request, before that, I may point out that the speaker will speak for about 50 minutes, followed by question answer sessions. I now request Mrs. Chandrakala Ratnakar, who is an ISRO scientist, a communication engineer, and a very active creative member, to briefly introduce the speaker for the today's session. Over to Chandrakala.
Thank you, sir. Good evening to all. Welcome for the special talk jointly hosted by Karnataka Physics Association and Creactive Gauribidnur. Today's talk is about introduction to foundation models and problem solving using data science. The invited guest speaker is Mr. Asitang Mishra. It's my privilege to introduce today's speaker, sir. His bio will be Asitang Mishra is a NASA Space Act Award winning senior research data scientist at NASA Jet Propulsion Laboratory. He has spent the last decade developing artificial intelligence and machine learning solutions for NASA JPL and providing machine learning expertise in interdisciplinary collaborations with Defense Advanced Research Projects Agency, Department of Homeland Security, National Cancer Institute, United States Geological Survey, and Chevron Incorporation. His areas of interest include data retrieval, search engines, natural language processing, graph-based algorithms, and time series analysis. More recently, he has worked in popularizing and infusing new technologies such as large language models into the JPL ecosystem. I welcome you, sir. I welcome once again all the participants to actively interact with the speaker. Thank you, Karnataka Physics Association and Creactive team, to giving me a chance. I'm Chandrakala. Over to you, Mr. Ashtang, sir.
Yeah, you may just carry on. Take over.
Thank you. Thank you, Chandrakala. Thank you for the introduction. And thank you, everyone, for attending and inviting me here. So when I gave a talk to KSTA, I mostly talked at least a lot about what my background is and what I do, what my organization does at JPL. Today, I'll do a quick introduction and mostly we will be focusing on the topics because we have some ground to cover with foundation models and data science. So we will talk mostly about the topic and a little bit about the introduction part. I'll make sure that I'll give you some context as to what do I do. So without any further ado, let's begin. So as you heard, I'm a data scientist, a senior data scientist at Jet Propulsion Lab, which I'll give you some background as to what we do there. Jet Propulsion Lab started in 1958, and it existed even before that as a lab for California Institute of Technology, or popularly known as Caltech. At that time, they were doing research in reverse engineering German V2 missiles, but later on, they ended up uh, building the first satellite for USA called Explorer-1. And that was the birth of NASA. And once NASA was an agency, they asked Jet Propulsion Lab to be part of it and be the first NASA center. Although because it was part of Caltech at that time, Caltech wanted to be part of it as well. They didn't want their elite lab to go to NASA. So it was decided that Caltech is going to manage JPL. So there was born JPL, which is a very unique federal research center, which is run both by NASA as well as Caltech. And more recently, it does less of the jet propulsion, but more of robotics and building satellites and ground communications, and also very popularly all the Mars missions. You may have heard of Curiosity, Perseverance, and a lot more before that, and the most recent being Perseverance. So that's kind of a quick background of Jet Propulsion Lab. Being an FFRDC or a federal research organization, we get to do a lot of cutting edge research, so which serves as a blueprint for, in general, NASA and other government agencies. We do a lot of collaborations. And so today I'm going to be talking a little bit about one such collaboration, which will give you some idea as to how data science projects start from just a problem and how they progress. And before that, as I promised, I'm going to be talking a little bit more in the technical sense of what foundation models are, and giving you some basic introductory idea about like how to work with them and what are the basic principles underlying these new technologies. So foundation models, let's begin. But before foundation models, we'll go a little bit in the past. We'll cover some basic principles, and then we'll come back to foundation models, because then it'll be much easier for everyone, because I know that a lot of people here maybe from the physics background, because the talk is by the physics Karnataka Physics Association. So I think that was my assumption. So let's begin from a slight beginning. Let's talk about deep learning first, what deep learning is. So deep learning is a specialized form of machine learning where we use artificial neural nets. Now, these artificial neural nets have been inspired by the brain neurons, as you can see in the picture on the left. And the bottom is the schematic representation of a node in a deep neural net, where you can see there is X1 and X2 inputs. These input could be anything, an image, an audio, a text, a video. It could be really any input that has been converted into the machine language. And then there are some weights to these connections. And really what the output that comes out of it is a weighted sum of these inputs. Along with that, we put some non-linearity on top of it. The reason why we put some non-linearity on top of it, because the model that gets developed then learns a lot of intricate patterns. And so it just makes your model more expressive. So it can learn complex patterns. And so you introduce some non-linearity to this weighted sum. So this is kind of the basic building block. It's okay if you think it's still very complicated, don't understand, but just understand that this is one node, and a neural net is made up of these several nodes. And you can see on the right, there is a deep neural net. It's called deep if there is more than one layer or more than one hidden layer. It's called hidden because it's neither the input layer nor the output layer. It's in between, although it's not really hidden. Now these layers are arranged in this way, which is that every node on one layer is connected to every other node in the other layers, on the layers next to it. Now, this is the most basic type of neural net. There are a lot of complicated neural nets as well, where there's not a complete set of connections. We will not talk about this. We will keep to the basics so that people understand slowly what's happening. What really happens is that you give the input slowly through the same type of calculation that I just explained with weighted sum and nonlinearity. The input goes through these different layers, and then an output is produced. The output, so the input could be the images of cats and dogs, and the output could be a prediction of if it's a cat or a dog. So it could be a binary prediction or a classification. Now, and we have some labeled data, so we know if it's a cat image or a dog image. And in the final layer, we compare the output that our model gives with the correct output or the ground truth. And we have a loss function which quantifies this loss as to how far is our output from the real answer. We do it over a batch of data. So such neural nets work on batch processing. We average out all these differences, called all the loss on a batch of data. And then what we do is something called backpropagation. In backpropagation, what happens is that we slightly change the weights of these connections so that next time if we give the same input, the answer is a little bit closer to the right answer. And slowly we tune this network so that the answer becomes closer and closer to the right answer. And so it learns. The theory of backpropagation, again, I won't go into the details of it, but there is something that helps us tune this network. So there's a forward propagation and then there's a backward propagation through which the network slowly starts learning and these patterns of how to map the input to the output. And that's kind of the basic idea of a neural net is. And from here, you can get very complicated. So before, again, going to foundation models, there's something I want to talk about is generative models. So what is generative models? You might have seen it. Recently, it's been very popular as people take a picture of themselves and then using AI, they convert their picture into some professional picture, which looks really amazing. They get a tie, they get a suit and everything, and they use it for their profile pics. It's again a very fun use case for this. So what is really happening and what does a generative model do? So a generative model, as the name suggests, it's generative. So it can generate a new data point which didn't exist before. So it can generate the face of a person where the person doesn't really exist. So these type of models are called generative model because they have this generative idea and capability of doing such a thing. To understand generative models a little bit better, let's first talk about embeddings. These are the basic building block of deep neural nets. And in the most basic form, what is an embedding is it's some sort of a mathematical representation of an input. So if you consider text, like this sentence called "I like oranges," do you like oranges? So you can convert it into a table like this. Apples, how many times the word apple occurs here? 0 times. Do I like oranges? And how many times they occur? So thereby you converting into this table where if you consider the English language has 30,000, let's assume tokens or words, then you can have this table of how many times each word occurred in this particular instance of data or in this particular sentence. So that becomes your mathematical representation of that sentence. And that is a very simple example of a vector. But fast forward, it is much more complicated these days, where you have a neural net, which is called embedding model, where you can input any image, any text, or any video or audio, and it has a capacity to convert it into a set of numbers, a set of fixed numbers. So a set of numbers with fixed dimension. So an image could be converted into 300 numbers, and each number is basically represent one dimension of the image. In the example I give you, the dimensions you can see clearly a word. So the dimension means something. Whereas these days, what happens is that you can convert it into a vector or a set of numbers where each dimension may not mean anything physical. or you might not know what it means, but it still represents some feature of language. Although using explainable AI, you can then probe and find out what that each feature means. But even if you don't know what each dimension in this list of number means, what it's doing is that it's taking any type of input and it's converting into a very compressed, expressive set of numbers. So now these numbers represent your image to much better to a machine. And these are called embeddings, or you can call them vectors. They're basically like a list of numbers that now represent your text, video, or image, or anything like that. Now, on the right-hand side, you can see the same, it's kind of the same image, where if you input an image or a text, and if you set the dimension for the vector to 3, it will give you 3 numbers. And obviously, because it's 3, you can represent it into a 3D space, and you can have some sort of a 3D latent space representation of your image. So each point in this 3D space will represent one image. And so you can have thousands or millions of images in this latent space, and you can visualize it. So this is kind of a little bit primer on what embeddings and what vectors are. Now let's move forward. So generative models, again, what else? Like generative versus discriminative. Discriminative used to be very popular. So if you're training a classifier for classifying, again, my favorite example, cats and dogs, because it was a very popular example in the initial machine learning world. So if you're trying to distinguish between cats and dogs, in terms of discriminative versus generative model, what a discriminative model does is that when you have, say, 1,000 examples of images, and you convert them into vectors, and then you have some n-dimensional latent space where these vectors are floating, or they have their own positions in this n-dimensional space. A classifier or a discriminative model, what we are asking it to do is, can you create a plane that separates this n-dimensional space so that if any new data comes, so before that, can you separate it in a way that all the cat data points are on one side of the plane versus all the dog data points are on the other side of the plane. So this plane itself becomes a way to distinguish between any new data. So if a new data comes in, we put it into that latent space, and we check if it's in this side of this plane or in that side of the plane. So that's kind of how a classification works, or what discriminative models are. Generative models, on the other side, what happens is that this model tries to understand the relationship between different data points. Why is this data point in this particular region of the latent space? Why it's not in this other region? How these points are related to each other? What do these different regions in this latent space actually mean? So a generative model can do it without a particular category of like cats and dogs. You can just give it a lot of data. It can put it into that latent space, and it can start understanding the underlying principles of associations between these different data points. So that's why you start seeing clusters. It starts understanding different clusters of regions in this space, and so it's called generative model because of that. And we'll see how can you use this concept. So on the left, you can see that this is a 2D representation of a latent space of MNIST dataset, which really contains handwritten numbers from 0 to 9. And if you represent them into a latent space in 2D, you can get something like this. And in a generative model, there is a decoder. And this is a very important part of a generative model. Again, a decoder is a neural net itself. The input is basically, we sample a point from anywhere in this latent space. And the decoder basically understands how to take this point and generate an image in this case, since the data is of a handwritten number, it can generate a handwritten number. And it basically understands how to decode the latent space into something tangible, an image. So what it's really doing is it's taking noise and it's converting it into a real world example. So that is, in the end, when you're training a generative model, you get a decoder that has the capacity to do that. You sample a point from a latent space and you put it into a decoder and it gives you a real world example. And this real world example might not exist before. It has seen, for example, 1,000 or 1,000,000 faces, but it might just generate a face that doesn't look like any of the faces it has seen. So what we basically say is that it now understands the different aspects of a human face. So that's the beauty of a generative model. Again, I haven't gotten into a lot of details about a lot of different things. I missed a lot of things on purpose here so that you don't get a lot of too much information and get overwhelmed. So now you understand this much. Let's go to something called a generative adversarial network. It's a very interesting concept. It was very popular as well. So let's see what happens here. So as I've told you in the bottom, there is a noise. You sample a point in that noise, and then there is a generator, which is again nothing but a decoder. It takes the noise and it converts it into an image, for example. Then on top, we have a lot of images of actual human beings. There's a data set we've taken from the internet, suppose. You take one sample from it. So in a GAN, there are two elements. There is a generator and then there is a discriminator. And what we will see here is how interestingly this pair learns by being the adversary of each other, by being the enemy of each other. And one thing you might have heard that to train a deep neural net, you need a lot of labeled data. So you not just need a lot of data, input data, but you also need labels for that data. And in general, such labeled data doesn't exist. So another beauty of generative models is that you don't need a labeled data. So you just need a lot of data. And we will make sure that we will make the problem statement in a way so that we will create that labeled data by being a little bit smart about it. So here we'll see that all we have is a bunch of images of real human beings and nothing else. We don't know who those images are. We don't know, we haven't pointed out to the machine if this is a nose, this is an eye, this is the beard. All we have given the machine is human faces and nothing else. And what we are expecting is that the machine learns the different features, associations between the eye and the nose and the hair and how a human face looks without giving it any clues at all. And with the GANs, we'll see what is the magic idea behind it? How are we making this problem a labeled problem without even having any labels? So again, a lot of training set. So what happens is that you take a sample from one of those actual human faces. Then you have the generator, as I've shown, a decoder, which takes a noise and that converts it into some human face. For now, let's assume that the decoder has not been trained. So it's garbage. So it takes the noise and it also outputs noise. It's not actually outputting a human face yet. So let's assume that in the first pass, it generates a noise, and then we have an actual sample. We give it to a discriminator, which is also untrained. So it doesn't know anything really about the real world. But we have given it a task that what you have to do is you'll get an image and you have to predict if the image is a real image or a fake image. Now, in one forward pass, again, you can imagine that the generator and discriminator, which are both neural nets, they will perform really poorly. But then what we will do, because we know which images are real and which images are fake, we will correct the weights of the whole network both generator and discriminator with back propagation, so that now next time it is closer to the right answer. And slowly by doing this forward and backward propagation, the generator starts learning how to generate photorealistic images, and the discriminator starts learning how to identify if it's a real image or a fake image. So they're both getting really good at their jobs. And so the discriminator is giving a challenge to the generator, and the generator is getting really good at generating photorealistic images. So it's challenging the discriminator. It's saying, I'm going to generate a fake image that looks very real. So in this way, by challenging each other, they're learning without any labels. So that's the beauty of a generative adversarial network. And this is one of the most popular example of a generative model. And I wanted to give you this one example of how things work. Now we are back to foundation models. I gave you all the primer so that you now understand what foundation models are really, because foundation models are generative models. They're based on the generative philosophy. So again, why is it called a foundation model? Is because these models are so large in scale, and they see so much data while training that they serve as a foundation for other smaller models and other downstream tasks. So some of the key features of a foundation model is that they're really large scale. They have billions and trillions of parameters, and they do like billions of trillions of calculations for like forward and backward passes. So they're huge in size. And not only that, they're trained on billions of like millions and billions of images or text, a huge part of the internet. And so what happens is that it helps a foundation model learn some of the underlying principles of images, of how the world on Earth looks, how different things look, how a car looks, how a monkey looks, how a Mars rover looks. And in text, it starts to understand the different associations between words, what even a word means, what is a parallel word in a different language for this word. It starts to learn all these things in an unsupervised manner, just because in a generative philosophy, it is seeing a huge amount of data. So huge amount of data means huge amount of patterns. And to learn these number of patterns, obviously you need the capacity of the model to be also large. So the parameter space of this model is huge. So these are very large scale. There's something called pre-training. What it means is that it's the unsupervised training. And again, we talked about the generative adversarial network, and you can see all you need is data. You don't need to label the data. You don't need to give it clues. You just need a lot of data. And you can do this type of unsupervised training, which is, in this case, it's called pre-training. Then there is something called fine-tuning. Fine-tuning, so once you have pre-trained your model, you want it to perform some very specific tasks. And those tasks are called downstream tasks. So if it has seen a lot of images of satellite imagery, now you want it to segment crops versus desert versus where is the cloud and things like that. So this is a downstream task. So you want segmentation, you want classification. So for that, you need a small labeled data set, and that is called and then you do a supervised training. So you use the same network, you use the same set of weights that you've trained during pre-training, and then you use a supervised loop to make it fine-tuning for that particular task. Usually what happens that a lot of foundation models that come in the open these days, they have been pre-trained on a large data set, and then they have been fine-tuned on several of these different downstream tasks. Most of the common tasks on which published researchers report their scores in NLP, in computer vision tasks, and stuff like that. So they end up training them on a lot of these popular data sets, on a lot of these tasks. So you do both in a foundation models. So what happens due to this is that you get something called transfer learning. So even though the model has not been trained on a particular data, a particular task or a particular domain of data, it has seen enough number of these patterns that it can adapt to any new challenge that has been seen without only a little bit of intervention and training. And so these models are very versatile and you can also see some emergent behavior that I'm going to talk about in the next segment, which is LLMs. But before that, this is an example of a foundation model. So Segment Anything was not open source, but this model is by Facebook. So on the left, you can see there's a CT scan, or I guess it's an MRI. I'm not clear on the difference of these two, but it's a DICOM image of it's a cross section of the abdomen. So you can see these organs, and right out of the box, this foundation model can segment different sections without even knowing what these sections are. But in a lot of cases, it has the language capacity and it can tell that this is the kidney, this is the liver. Although with medical images, it's a little bit poor, but with real world examples of things, of the camera images, it's really good at segmenting and tagging these things. The inputs could be obviously in the image, and there could be some prompts as well. You can pinpoint the area where you want to generate the segmentation mask. You can give it a bounding box saying generate a mask within this bounding box. You can give it some rough initial mask, or you can even say what you're looking for in an image, and it can create a mask around. It can generate a segmentation mask. Very useful. Again, you might be thinking for a lot of different downstream tasks, and it happens right out of the box. So that's the beauty of it, and it's been trained on on billions of masks and millions of images, and that's why it's able to do it so well. Again, another example is DALL-E, which again very popular because people are writing all sorts of prompts, and it's able to generate these images, like picture of an astronaut riding a horse, and it can just generate these images. Again, a diffusion model, but it uses a different technology called diffusion, which in general, in practice, what happens is it works better than generative adversarial networks. The idea is very simple. You take an image and you slowly start introducing noise, and then you ask your neural net to progressively denoise your noisy images. Now, you already know the right answer in this case, like you already have the denoised images, so you have something to compare against. So you can generate a loss metric, a loss function, and then you can do a back propagation to again fine tune your model to become better and better. So that's an example of diffusion. Again, another popular foundation models are large language models. So ChatGPT is a popular one recently. You might have used it. If you haven't, I highly recommend using ChatGPT to see how amazing it is with its language capacity and capability. So the use cases are it can do text generation, can do translation, question answering, text classification, named entity recognition, code generation, content recommendation, and a lot of more things. Now, I was talking about an emergent behavior that why these foundation models are so versatile. So this is from a talk I gave in IUCA in Pune. So I took this text from their website, and I asked ChatGPT that, can you organize these things into organization location names? Can you extract these person names, contact details, and such? And just me asking it was able to do it. Now, I want you to understand the beauty of this in natural language processing research is that people have done so much research in named entity recognition. It's a task in itself. It's an area of NLP in itself. And this foundation model is able to do it without being trained on this specific task right out of the box. So you can see how amazing foundation models can be for any new tasks. So you can create a new task and you can give it to it, and it can do it just because it understands language and the underlying principles. So that's a great time to this is a great time to be an NLP researcher, I would guess, or elsewise too. So how are these LLMs trained? Again, a very simple example. It's a very basic and simple idea. Again, the implementation of it is way more complex, and we will not go into it. So you have a lot of text online, and everyone has a lot of text. What you do is you mask some of these tokens or words, and you ask your model to predict those words which were missing. So there are two ways of doing it. There's masked language modeling and there's causal language modeling. They sound very different, but they are not. In masked language modeling, you just mask a bunch of these words, and the neural net tries to predict what those missing words were. And the causal language model just tries to predict the next word by looking at the previous words. So these are the two different ways in which a language model is trained. But then in the end, you can see how many wonderful things it can do later on. But the idea is so simple and basic. And then that's the beauty of it. So that kind of concludes our foundation model section. And I see that it's 8:08 right now. And so I will move a little bit faster in this next segment, where I will give you an example of an end-to-end from problem statement to a solution or a project in data science, and how this interdisciplinary data science work. And again, since JPL is a federal research organization, 10% of the things that we do are not necessarily related to space, but they could be core research, as long as they could, then the results could funnel back into space research. So one such project where we helped another organization, where you might have heard of United States Geological Survey. One of their main purposes or action items or tasks is to do mineral resource surveys, mineral resource assessments, how much mineral is where, with what quantity, and with what purity, and they need to do it. So recently Congress wanted them to do a critical mineral survey for all the critical minerals, and they wanted them to do it within like 5 to 10 years, whereas they said it might just take us more than 50 years. So how do we do that? They went to DARPA, which is the Department of Defense technical branch, which does a high risk, high reward type of projects. They got Jet Propulsion Lab involved because we had certain relationship with them. We worked on a lot of technology projects before with them, and hence this task was born, where we wanted to understand what these USGS scientists do during their mineral assessment process, and how can we really help them? How can we bring automation to their day-to-day work? And so after a lot of back and forth and discussion, after a while, we came up with a challenge called Artificial Intelligence for Critical Mineral Assessment competition, which was made public. And we asked people to solve this problem, just to see how well they can solve it. But before that, we sat down with the USGS folks, and we tried to understand what do they really do in their day-to-day life when they are doing a mineral assessment, and where are the bottlenecks? Where can we bring automation? I will not go into all the details of all the things that they do, but we came up with this nice chart of how the things progress during a mineral assessment. And we understood that the biggest difficulty for these scientists was compiling and finding the data. So for doing an assessment, what they do is they try to find their previous reports. They try to find reports of assessments from government, local government or state government agencies, and also private industry mining partners. And as you can imagine, everyone has these reports in all sorts of different formats. Sometimes they don't have a database for images. There are tables within PDFs, there are images, there are maps. Then there is text that talks about the relationships between them. So as you can see, this information is not digitized. It's not machine readable. It's not machine understandable. A human needs to go through these thousands or hundreds of thousands of pages of reports to find these relationships, this knowledge, and then based on this knowledge, they're doing a reporting. So you can imagine how long this might take for a human being, or even like 50 or 100 human beings to do it. So it's a time-taking process. So we wanted to automate this compilation of and gathering of data. So converting everything into a digitized way. We came up with a set of challenges or a machine learning problems. So we did some brainstorming as to what kind of machine learning problems can we really come out with this problem statement. So here are some of the examples that we came up with. You can, when you see a scanned map, there are a lot of features. These colors represent some feature on the map, and the legends, they describe the feature, and these colors represent whatever is on the map. And as a human being, we are really good at doing this. But as a computer, it's very difficult for me to not only just segment these different colored parts, because these colors, at least in this map, they're all solid colors. Sometimes there's gradients of colors. Sometimes there's no color, but there's patterns. And there's always something in the middle. There's rivers, there's mountains, there's things written in the middle. So a basic algorithm can do only a basic job at this. And it can bring you only like 60% of what you want. And it might even be useless for you. So this was one challenge we thought would be useful, is to, can a machine look at these legends just a human can do and associate it with the right pattern or the right color in the map. And that was kind of the one challenge. So and it was also a one-shot learning task, as we call in machine learning, where you give it one clue, and based on that one clue, it should be able to do some predictions. Then there is georeferencing and georectification. So if a scanned map, can I place that map in the right place in the globe? So match the center of the map to the right place. But not just the center, you have to actually map the map on the globe, you have to sometimes scale it, fix the projection, rotate it, and so that the rivers match the rivers, the mountains match the mountains, the geopolitical boundaries match. So there's a lot of different things that you need to take care of. And what are the clues here in the maps? So you get sometimes the coordinates written on the map. Again, you have to remember there's more than 100 types of coordinate system all across the world, and they change over time. So you don't know what kind of beast you're really dealing with for a particular map, when it was produced and when it was used and things like that. Everyone just tries to use some different type of formatting. And what are the other clues? Other clues could be the geopolitical boundaries, the shapes of the rivers, and things like that. That could be a really good indication of how to place the map on a larger map. But again, this is the biggest gap in research in such type of georeferencing and georectification. And the hope is that at some time in the future, some of the foundation models will get so good at understanding the geophysics and the shapes of rivers and such, that they will be able to do it right out of the box. But right now, there's no such technology. The other clues could be the names themselves. I think that's a really good clue. But again, it doesn't really give you the scale of the map. It just tells you that it roughly belongs to this region in US or India or somewhere else. So we didn't ask people. So that was kind of one aspect of it. So georeferencing and georectification. Some of the challenges were table structure recognition, understanding what kind of data is in the table. I mean, first of all, recognizing there's a table, recognizing the structure of the table, recognizing the semantics of the table, what information lies in the table. Can you relate this information to other things in the text, in a PDF, in a report? So a lot of challenges. Then map area segmentation. So you have a map, but do you know, how can a machine tell if this is the map area, this is the legend, this is where the scale of the map is, this is where the general information about the map is. It's in itself, it's a task. So these were some of the candidate challenge problems that we came up with. Although I can say you can create hundreds of machine learning challenges from that one challenge that these scientists were facing. But we had to narrow it down to some challenges so that that could be solved in time, of course. Out of those, we only selected 2 for the competition because we had limited resource, and maintaining a challenge and then evaluating a challenge in itself is a challenge. So we selected 2, which was the map georeferencing. We asked, we'll give you the maps and use any kind of clues you want, but place it correctly on the global map. And then the feature extraction, we said, we'll give you the legend, we'll give you each item in the legend, we'll give you where these legends are, and we'll give you the bounding boxes around these legends. Can you connect them to the right place in the map? And can you segment that part? Again, you can have some very baseline solutions for this. As some of you might already be thinking, can you match the color and stuff like that? But again, those are the baseline solutions that everyone kind of came up with. We ourselves provided that baseline solution so that people don't start attempting the most basic solutions. So in the end, a lot of people tried to use something very creative. Again, I won't go into the details, but these were the 2 challenges that we came up with. Now, from the machine learning perspective, what are the different challenges that you face in such a problem? As you can see, defining and designing the technical challenge itself is a big task. So at JPL or even DARPA, none of us were geological scientists or geochemical scientists, or we knew exactly what these USGS people, when they're doing critical mineral assessment, what they do. So we had to quickly learn that. We were not experts of it. We were experts of machine learning and how machine learning works, how you can automate things. But we had no idea what these guys are doing. So we had to learn that so that we could recommend them in their own turf what could be done, what could be automated, and what things. Again, you have to understand with technical challenges that you have to find a technical challenge to solve that is not unsolvable. So it's not so difficult that no one is going to solve it. You know that the data doesn't exist, the technology doesn't exist, or it shouldn't be too simple, so that you pose it as a challenge, and in a month someone is coming and saying, oh, we already solved this challenge in our company or as part of this paper, and you should have contacted us instead of doing all this effort. So we had to be very thorough in doing our market research as to, okay, no one has solved this problem. There is an actual gap in technology here. And also that this challenge is actually viable and people can actually solve it given the right amount of guidance and money or data. So that was basically some of the challenges that we faced and overcame. Then defining the scoring metric. Again, with these 2 tasks, one of the tasks was a pretty popular task in machine learning and this area. The other task of feature thing where one-shot learning with label by looking at the legend, it didn't exist before. That there was no machine learning task like that before. There was at least one rough, vague paper about it we found. So we had, and then there, not only we asked people to identify an area as a feature, but align feature or points like mining points or points in the map as well, based on the legend. So how do you really define a scoring metric where if they give you a right answer, or if they give you an answer, how do you compare it to the right answer? So doing it visually so that it also is explainable, it makes sense to people. So how do you define that scoring metric? It was a big challenge and we ended up doing it. We ended up creating an entirely new scoring metric for it. Then again, you have to automate these things. Every time someone submits something, it should be quick. The evaluation pipeline should be in place so that you click a button and it gives you the evaluation for any new data. You have to do data preparation. You have to make sure that everyone understands that they have to submit data in a particular format. You yourself have to understand what kind of data formats you need so that later on the evaluation and everything could go smooth and it's not overcomplicated. People don't do anything stupid because you have made the challenge too complicated. So a lot of things to think about, but that's exactly what makes this challenge so challenging and so exciting. Again, annotating a lot of data. The data didn't exist. The labels didn't exist. So we had to annotate it. We first thought was, let's have an army of interns, make sure that they do it for us. But in the end of the day, we ourselves had to sit down and do the annotation to some extent. And so it again became a fun task because everyone was doing it. So again, that was kind of a small brief into problem solving. So later on, after the challenges happened, and we announced the winners, what DARPA did was based on these preliminary results, they understood what is solvable, what is not. And then they created a larger call for proposal where after the call for proposal, it became a multi-year project. And now it's still, that project is going on called Critical Mass. And so you can see from a problem statement and a challenge someone was facing to a big multi-year project, how things progressed. That's pretty much all I had to plan to present. Now, thank you very much, and I'll open things up for question.
Thank you very much. There's time for a few questions. If there are any questions or comments, you can make them. Already I see several hands going up. Jagdisha, you can ask your question.
Sure.
Yeah, please go ahead.
Content-based image retrieval for map feature extraction instead of struggling so hard with that.
No.
That is one thing. Second thing is we have to make use of some collaborations with Planet Labs, small satellite institutes in America. Okay, there is a private organization, of course. They are putting the data, daily data into their websites free of cost, with say some 1 meter resolution data also.
No.
So how it is so economical for them to do it? So we should have a collaboration between India and them, either through private or government. Is it possible for you to help in that aspect?
Absolutely. Like I like how we usually at JPL work is all through collaboration, and that's kind of also one of my area of expertise of collaboration with other organizations. So it's very much possible, and if the data is open and it's allowed under some license for you to use it, then there is a chance that you might not even have to do a collaboration with them. You can use the data, make sure that it's under the license of the policy that they have made the data open source with. And the biggest challenge is what do you want with the data? So if you want to train a particular model for a particular use case or downstream task, the biggest challenge that even we have faced in the past and sometimes we are facing is how do we train these models? Because a lot of these foundation models are so big and they take so much investment in terms of money that, but there are several ways in which you can overcome that. A lot of these industrial partners like IBM, Microsoft, they want collaborations with big institutes so that they can showcase their capacity of computing along with some real use cases. So I'm definitely open to spearhead some of these collaborations if you want.
Yeah. Deep learning models we have used for Bangalore. NRSC has used for using ResNet and things like that, some hardware, maybe ascent gradient algorithms.
Yes.
I have found no increase in the capability of determination of the vegetation here. See, there are several different parks here to classify the vegetation as a whole. And it is not verified also. Of course, it is a refined value. One park looks like two parks now, two different vegetation, three with different vegetation.
Yeah.
Either we have verified, nor anybody else in the world has verified.
Yeah.
So actually, the applications on the Mother Earth is more better than going for applications in the medical field.
Yeah.
Because medical field images are far away from those doctors, they don't even look at the images properly. By experience, I'm telling you. A surgeon, he could not even identify one small mistake in small intestine, and he was getting scoldings from an expert in that. He is also unpaired in digital image processing. So, can you have some proposals with us in India to do a practical application on the Mother Earth for identifying either the crops or vegetation? Of course, my friend is there in USGS. He is working on NASA using same deep learning techniques. So we are at loggerheads.
Yeah.
So he simply uses it because it gets approved by NASA. So I'm sorry, I'm not raising any objections. Because the field of deep learning and machine learning is so large, if I go to the mathematics of that, it is very, very heavy. Very heavy. Just a suggestion.
Shall we go on to the next question? Next question, please, by Venkatraman.
Sir, before we go next question, may I ask the previous speaker to introduce? It will be better because others will not. Professor Jagdisha, if you don't mind, can you introduce and then we'll go to next question. Those who ask question, please introduce in the first minute or second.
I worked for remote sensing applications through NRSC and RRSC. NRSC Hyderabad 10 years, RRSC 25 years. And
thank
then,
you, sir.
Retired, application scientist.
Thank you, sir. Then we'll move to the next question.
Venkatraman, please ask a question. Venkatraman, please, you can go ahead and ask a question.
So, yeah, sorry, can I begin?
Yeah, briefly.
So, I'm Venkatraman Patnaik. I'm in grade 6 studying under Cambridge Board. I'm an independent researcher trying to study in space science since the last 3-4 years after getting interested from Chandrayaan 3. And I'm also a tech speaker and have spoken multiple platforms as well. So, I had a question. So, firstly, before I ask my question, just to clarify, a generative is not truly generative, right? Because according to your information, it still relies on discriminative systems.
You're right. There is aspects of generative where if you don't add certain features to it, it will just generate images that it has seen before. So there is a way in which you introduce some sort of Gaussian sampling in the middle, which makes it a little bit diffused in the sense that instead of understanding a mapping between a point in the latent space to an output image, it starts to understand not just the point, but a region around it. So it starts to understand that any region around this point should also look similar to this particular point. So you're right, they're very related in that sense.
Okay, and now coming to my main questions, I have 2 of them. Firstly, we have seen the
I
extent.
request you to wait for some more time because let's have chance for other people to ask questions. Please wait for some more time. Let other people also ask questions.
So,
May Professor B.K., may I ask you to, if you don't mind, let this boy finish so that we can go to the next.
He has 2 or 3 questions. Okay, go ahead.
Yeah.
Questions.
Okay. So here's the thing. So Venkat, ask me one main question that you have, and I'll answer it, so that others are allowed. And then in the end, if you have time, we'll come back to you.
Yeah, other people are waiting. So.
okay, sure. So, I'll just ask one. Okay, we'll come back to the other then, if possible. So, my question was that when we are taking such a system to say, to what extents and applications that JPL does, say, taking it to a different planet or a different system, and then say it has the job to identify rocks. So how can one basically try to learn its properties? Because what I've seen in your slides, it can try to differentiate, but we are, say, going to Mars, but we don't know its rocks, right? So How can it possibly work?
I think what you're asking is a very basic philosophical machine learning question is that how do you know something that you don't know? So if you already don't know what kind of composition of rocks in Mars and what kind of different properties, because it's a completely new planet. So what happens, and you're completely right in posing this question. So what happens is that all we do as humans, what we can do is we can judge anything new based on what we know before. So here also we are doing the same thing. We know that something is a rock versus something is a molten rock versus something is dust and things like that. So some things which we have high probability that we almost know what the structure it might be. So what we know already, we're trying to map it to Mars as well. But we don't really know. And that's why there's the Mars Sample Return Project, where they will get the actual sample from Mars, get it here, analyze it. But before that, we still want to do something, right? We don't want to sit and be like, we don't know, because all we have seen is what we have seen on Earth. So we still want to do some things and compare it to how it was on Earth. Maybe it will be a little bit similar on Mars. So that's kind of the basic basic assumptions we go with.
Okay. So in short, we first have to run on assumptions, and when we get something that can be imprinted by developer to the AI machine or robot, in
Yes.
that case only it can work efficiently.
Yeah.
Venkat will come back to
Just
you.
like
Venkat,
in
the other-
Bayesian, you add to your evidence. So you have some idea, but you keep adding to your evidence when you see new data. So that's it.
Thank you, sir.
Yep.
Srinath, please, you can ask your question.
Yeah, thank you. One information and one question. Information is that currently the Japanese lunar mission is getting landing another 10-15 kilometer away from the moon surface. So
Oh,
surface
amazing.
is information to all.
Very interesting.
My question to the speaker is with respect to academics. In US, because of course in the research institutes like JPL and NASA, AI and ML may be at a higher level of utilization or the implementation level. When it comes to the academics and teaching to the, whether it could be primary or whatever may be the education system there, how is it being looked at it? That is one short answer I'm looking at it. Second one is legally how it is being framed to prevent the setbacks or whatever negatives of the AI. Two short responses.
Okay. Very good questions. I'll try to give short answers. The first question, I would claim that universities are doing much better job at and let me know if I'm audible.
Yeah, sure.
Okay.
Audible.
Okay, so universities are doing much better job at focusing on AI and ML compared to government institutions. Government institutions are still lagging behind a little bit. JPL, there's a very specific group of people who are pushing the boundaries. But in general, just like an old government organization that has been going for a long time, we have this similar problems with any other country. A lot of things don't want, a lot of people don't want to change. They are scared of new technology like AI and ML. And but these are changing. These disruptive technologies are making sure that so I think a big issue was of trust. Can we really trust? And someone said that some of these deep neural nets, they don't work, which is true. But every year they work a little bit better. So when you get a lot of confidence in the results of something, then people say, oh, let's use it now. So sometimes organizations like NASA, they need that type of that 100% proof that it's going to work. That's when we will investigate into it. So we are trying to change it a little bit, our organization within JPL. Second question, and also universities are much better because they have a little bit more free reign over what they can try, what kind of fundings they have. And it's basically their job to try new things and teach new things. So they're doing a little bit better in US with AI and machine learning. Private industry is doing even better. So
We move on to next. Professor Srikanta, you may ask your question.
Oh, sorry. The second question was
Legal aspects, preventive.
legal aspect. So someone said, and I might agree that this year is going to be the age of the year of like people suing or cases like legal cases against these models. So ethics is becoming largely a big part of discussions even at NASA as to we can't just use something. We have
Professor
to be
Srikanta,
ethical
now you
about
can.
it. So people and the
Good evening.
lawsuits are increasing.
We'll go on to the next question, please.
Yeah.
Good evening,
Yeah.
Vishnu. I have two questions actually.
Yeah, please.
One is, while explaining the generative models, you
Yeah.
give the example of face recognition. I mean, discriminating between the real face and the fake one.
Yeah.
Okay. There you said that you are suppose you give just you say human face. Okay. You said only human face is the what you give the clue to the AI.
Yeah.
You take my own face, for example.
Mhm.
You take the measurements like, what's the size of the nose, then distance, etc., etc. Suppose I give all the clues to the AI, let's say, then
Yeah.
it generates a face. I mean, exactly like it resembles my face.
Yeah.
But there is one again real face. So how does the discriminator distinguish between the fake and the real? If I do that one.
So that's something. So there are things which humans are good at, and then the assumption is that there are things that machines should be good at. So this is a question where the how is a little bit unclear as to if you just change a little bit features of your face and you will ask if this is a fake face or a real face. I will say that a model might classify it as real and some models might classify it as fake. But the idea is that as long as the model understands some underlying principle of that there is a slight blemish on the cheekbone is a little bit different from most of the cheekbones it has seen compared to the eye. So the idea is that it is learning some very subtle underlying principles, and you're right. At one point, it will stop. The generative models will become so good that the discriminative models will entirely fail to recognize if this is a fake and real. And this is a big problem right now because of the fake news and all the fake photos generated on the internet. So it's actually a research area in itself these days. So really good question.
Yeah. Second question.
Yeah.
In the view of this, AI is doing so much, right?
Mhm.
So you are familiar with the Indian style of teaching and learning.
Mhm.
And I think you are familiar with that.
Yeah,
Okay.
I've studied here.
Now, how do you think that the teaching style has to be changed, at least for the next generation, in view of this AI coming into the picture and all that?
So this is my personal belief that when in India, and then I was talking to someone as well in terms of like how Indian researchers publish versus American researchers publish, is here in India, we are very careful about the mathematical aspects of thing. We want to make sure that the mathematics, the theory, the logic is crisp, and all this is backing some result. Whereas there is another type of research which can happen where it's entirely applied. You change things in terms of you understand different technologies as black box. You understand what it is used for. You try to use it very intelligently to create experiments, see results, evaluate results. And in the end, you can still publish things, you can still analyze your results, you can think logic. And then if there is a reason to go into very, very detailed mathematics of it and theory of it, you then do a back learning approach. In India, usually we go from very solid mathematics to application, but I personally like where you start in the middle. So you don't have to understand literally everything, but you start using things, you start applying things, and you do some sort of back learning based on your use case, based on the technologies you use. So that kind of research moves and that kind of education moves very fast, as well as it becomes very interesting to people because you're solving real world problems, you're giving them real world examples. And also when these things are hands-on, they can do things and see how it is changing. So for example, Bayesian mathematics, if you start by the theory, someone will just give it up and say, I'm not going to do Bayesian anymore because it's, but if you start giving them real world examples as to why you need to do Bayesian and things like that, and then even give them a problem that elucidates that, and then go into the mathematics after that, they might learn a little bit better. So that's kind of how I personally feel like people can learn faster.
Okay. Now I have a few somewhat
answer.
naive questions.
Yeah.
One of them, let us say you take a photograph of a moving object. Can you build up a model where you remove the noise effects and recreate the image? That is one thing, real image, one thing. And
Mhm.
secondly, supposing you hear an encrypted message, in the foreign language being transmitted from one place to another place. Is it possible to decode that and get the real message? Encrypted message, can they be decoded using your models? Thank you.
I would say both answers as yes, potentially in the application sense, and I will tell you why. So the blurry image to a real image of a moving object, when neural nets are considered, it can learn anything, any type of mapping, as long as you give it enough data. Now, with blurry images and real images, what can happen is that you need the model to learn what kind of blurry images can be produced by real images. So you can do simulation where you can take a lot of real images, you can make them blurry, and then give it to the as a challenge to your neural network.
Remove the noise.
Starts understanding the counterpart of a real image, and then when you reverse it, you basically get a model. Similar thing can happen with encrypted language. Language inherently has some properties like human languages.
Yes.
Inherently have some property of distribution and such. In a lot of language, you use these words. So the probability distribution of words in a lot of languages are similar. So if you convert two languages in a latent space with same number of dimensions, then you can actually map these languages somehow to overlap. And when you map them, you'll see that the words which represent I versus I, they're aligned. There's actually some translation papers of
may I request here an interpreter?
neurotranslation that use this.
Asitan,
Sure.
can you put the YouTube live slim touchdown, because it's another 4 kilometer, 5 kilometer touchdown they're showing. Since you're sharing screen, it may be beneficial. Sorry to deviate. It is Japanese landing. Put it on YouTube. We can anyhow we are the conclusion.
Let me
YouTube
Yes,
slim live.
I have
SLI.
one question. Please,
Yeah,
could you?
You please proceed, sir. You can ask question. But
Yes,
that
sir. Here I have one question, please.
Nagaraj, okay, please ask.
Yes, sir. Yes, sir. Professor Mishra, in this AI to construct a beautiful face, will they follow that golden ratio? I don't know whether you heard my question or not. Yeah,
I
golden
heard. Can you hear me?
Not clear,
because
please.
they are talking that if the face is somewhat very good and it is based on golden ratio, they are telling. Yeah, will they follow the same technique even here also to construct a very good face?
So first of all, does anyone have the link to the touchdown? Because I'm not able to find it. I can share it.
I don't have that. We don't have.
So if someone can find it, then I can play it. But and then someone else can also share their screen because I'm done here. So please do. Okay, so meanwhile, I can answer the question. Uh,
I think Srikanth is trying to get the.
okay, so the golden.
Yes, yes, yes.
Okay, it's being played, is it?
Nice, very nice. So, so sir, like the golden ratio thing is that we as humans, we have analyzed that what is beauty, and in the endeavor of understanding beauty, we've made a hypothesis that if it has a golden ratio, then it will be beautiful. So it's not a truth, you know. It is basically a hypothesis that most of the people might believe, but it's very hard to prove it. But let's entertain that it's true and it happens. Then what you can see is that because a neural net doesn't know about the golden hypothesis, golden ratios, all it knows is that it has seen a lot of photos or images. And what it can do is it can generate a realistic human face. So it has no idea of what the golden ratio is, but you can check if how many faces that it generates has a golden ratio. Also, it is seeing all sorts of faces, you know. So it's not necessary that we are only feeding the data for golden ratio faces in it. So that if we do that, then it will generate golden ratio faces.
Only those figures only.
So
Okay, thank you.
Not everybody has a golden ratio, isn't it? So,
Okay,
we
thank you,
really-
thank you, Mishra. Okay.
Yeah.
Okay, shall we wait for that touchdown or shall we close the meeting?
Up to you guys.
Sir, it's only matter of 5-6 minutes.
Okay.
Matter of 5-6 minutes only.
In the meantime,
Because it is
then
a 500 meter.
any question,
It
any
is a
other questions
500
or
meter
comments? Any other questions or comments by any other participants? They are welcome.
Yeah, please ask me more questions. The questions are very good.
And one more question, if you allow me to ask.
Yeah, please go ahead. Go ahead.
Yeah, you are telling
Please.
that to convert into a vector. What is the purpose of converting everything into a vector? I didn't understand that, even though I am basically a physics teacher, but I didn't understand how you convert that into a vector.
Mhm. So, let's see. How can I explain? What a vector is that vector is like a compressed. So let's see what in the application it is used for. Maybe then we'll understand why it's necessary. So I have an image, and there is something that converts the image into and so suppose I've set the dimension of vector to 300 dimensions. So it will generate a 300. It will generate 300 floating point numbers for me. So it will take an image and it will convert it into a flat another image, and it can convert it into another vector. Now, if you have two images, what is the way in which you can compare these images for saying that these are similar images? What will you do if I ask you to do this? Can you use a machine simple algorithm to check if these two images are of the same person, or they are of a human, or they are in any way similar? It's a very difficult task to
No, probably
do
what
this
we should
in a machine,
understand by
to check
vector
if two
is
things
a
are
set of
simple, at least with
organized
images.
numbers, a set of numbers which depict, which occupy a point in your data space. Probably that's what he means.
Yeah, so
Mostly
that's
touched on
true.
now.
But the practical application of why we do that is that when you have a vector, what a vector means that it's a compact representation of your image. So you can say it represents the idea of the image.
Okay.
Okay.
As to each
Close the class and,
dimension,
people can watch this one in YouTube.
so each dimension might mean something. The first dimension might mean that it's a human face or not. The second dimension might mean that does it have a nose or not. The third dimension might mean that if it has a NASA background or not, or something like that. So each dimension might mean something. We just don't know what it means in terms of these embeddings, but they mean something very specific. Now, what you're doing is you're taking an image and you're converting into this vector where each number means something. We just don't know what it is. But if we have two such numbers, then we can compare the first dimension to the first dimension, the second to second, third to third. And if we aggregate over it, we can generate a metric saying these two match by points by 60%. And then you can actually see the images and you say, oh, this is the same person. One was just an image of the person when he was old. One was when this person was in school. So this is the practical value of converting everything into a vector.
Okay, sir. Thank you. Thank you.
Yeah.
So you have to
Thank you.
understand that as a set of numbers.
Sir, last only one small comment is a short, very short comment.
Yeah.
In fact, recently, now that in what is happening in India, we are all worried. I mean, very enthusiastic about Sri Ram Temple, no, and Ayodhya. So for the last 1 month or something like that, a very beautiful, handsome face of Rama was in circulation in the WhatsApp and all that. I mean, how he has looked and all that.
Yeah.
I mean, as a boy or something. So then I was also actually thought that, okay, this is the real face, but how could we get that? But later on, we came to that it's a AI generated, where what Nagaraj was telling about the golden ratios and all that, everything has been taken into account, and a very handsome face was generated using AI. So that's could really very handsome Rama, actually. Yeah.
So that's the thing, sir. Like it's
Yeah.
like the sky is the limit with these kind of technologies, but then again, it's not a replacement for common sense, which is like we know as human beings that it can never generate the actual face of Rama or like anyone who's existed before, who we really don't know unless we have the bone structure or some more analysis, or we know that he belonged to a particular what region of India he belonged to, who were the original people who lived there. Can you actually take all the faces? But even then, it will generate a generic face, a generic beautiful face. It might not be of the same person. So, but it's fun.
Perhaps an artist can do a much better job than AI in particular case of
so I guess
figure. Artists are so many good artists are there. They can figure fine.
So that's I think exactly the word.
Professor BAK and Ashitang.
It's not a realist.
Yes.
BAK and Ashitang, it is just information now. SLIM is successfully on the moon surface. They have declared it.
Nice.
Finally, we are able to get that information.
Very good.
Happy to celebrate. Maybe you can conclude, sir, because we have taken more.
I request Professor Nagaraj to propose a word of thanks briefly.
Yes, sir. I think it is wonderful evening. In fact, I thought that how I could understand this. At least to some extent, I have understood after asking and discussing about these things. Anyway, you have presented very nicely, and thank you very much for your time. You have accepted our invitation and you have made it. So thank you once again, and thank all the members, especially the creative and Dr. Srinath. He has helped us to conduct this program. I thank him. And I thank all the members of our association, KPA. Thank you very much, sir.
Thank you all
so much.
I'm glad I was of you. Come back for the next meeting. Thank you.
Yes, sir. Yes.
Okay.
Thank you.
Thank you so much. Thank you very much. Thank you for having